Okay, so hello everybody and welcome to the last lecture of the day. It is my great pleasure to introduce our speaker, Stephen Melczer. So Stephen is an assistant professor at the University of Waterloo, Canada. He's an expert in combinatorics and in effective and computational mathematics. Among many other contributions, Stephen wrote a very beautiful textbook entitled An Invitation to Analytic Combinatorics. And today he will invite us to a journey into the world of enumerative combinatorics. So please, Stephen, the floor is yours.
Thank you, Aline, and thank you to the organizers for inviting me to give a talk in this very interesting and nice workshop. As Aline said, today I'm going to give you an introduction to the field of enumerative combinatorics, which I think is a very beautiful field of mathematics and computer science. In particular, as we'll see, it takes a lot of techniques from different areas of math, so you get to learn a lot of interesting mathematics and apply it to interesting applications. Before we get started, I also just want to mention that I do have a 1-month-old baby in the house, so if you hear screaming in the background, don't worry, it's probably just the baby, and it will, he will calm down soon. Okay, so let's get started. So I split this talk up into a few different parts. So part one will just be discussing some of the background for what are the basic objects and tools that we have in enumerative combinatorics. And so first we're going to talk about discrete structures. And I want to start by saying that a modern view of the world, not necessarily mathematics, but just the world in general, consists of studying discrete structures. The discrete structure is like a big structure that's made up of smaller components. So there's some indivisible components that comprise the whole structure. So for instance, very famous one, of course, DNA. In modern times, we now know that DNA is a sequence of nucleotides. So this here is a sampling of chromosome 1 from the International Human Genome Sequencing Consortium. So this is basically a gigantic sequence of A's, C's, G's, and T's, which are different nucleotides. Aside from ignore these ends at the beginning, this is some extra spacing information that I don't really understand because I'm not a chemist or a biologist, but you can essentially think of DNA as a really long sequence of 4 letters. And if we want to know something about, interesting things about DNA, or if we want to know, how closely related two people are, this is basically a mathematical question about this structure of A's, C's, G's, and T's. So we'd like to know if you see a certain pattern in this very long sequence, very, very long. It's 250 million length almost, just for one chromosome. And of course, humans have much more than one chromosome. DNA this is a perfect example of this discrete structure. It's a long sequence of 1 of 4 letters. And so to say something about DNA, we might want to say something about the mathematics of what's the probability a certain pattern would appear in this sequence, or if 2 people have the same kind of sequence, a subsequence at a certain point, are they closely related or not? Okay. So this is one type of discrete structure. We'd call these words maybe in an alphabet or finite sequences. Another one, of course, that everyone knows is the internet. So the internet, we can view this as a graph. So a graph is a discrete structure that consists of vertices or nodes, which in this case are websites, and then links between them, which are sometimes called edges, which are usually called edges in the mathematical context. In this case, that would be links between websites. So I took this beautiful picture here from Wikipedia, which is a partial map of the internet based on data from 2005. And so each of the little dots here that you can basically not even see are different websites or IP addresses, and they're connected, and there's actually the length between them is the distance it takes to go between them. So there's actually some kind of, it's telling you something about how connected the websites are and how close they are together and things like that. It's very interesting. But the point is that if we want to model something about the internet, we can study it in terms of this mathematical structure of a graph, which consists of these vertices and edges between them. Now, graph theory is a gigantic subject, so I could spend all day talking about different applications of graphs. I just want to mention one more, though, because it's one of my favorites, and it also shows sometimes the power of enumeration. So this is talking about chemical bonds. So chemical bonds or chemical formulas you can also think of, in some sense, as a graph. So I don't know how it is around the world, but in Canada, when you're in high school, you have to do these problems in high school chemistry where they give you you have some chemical with like some number of carbons, some number of hydrogen, some number of oxygen. You have to balance out how many there are so that they can fit together with the properties that these different chemicals have, these different molecules have. And so in particular, maybe you remember, maybe you don't, but if you have a carbon atom, carbon basically can bond to 4 other atoms. Hydrogen can bond to 1 other atom. Oxygen can bond to 2 other atoms, and there's other rules for the different atoms, the different elements. Sorry. And so what you can do is you can think of a chemical bond as a different kind of structure. You can think of it as a graph and then study these kinds of structures mathematically. So this is an article here by Cayley from 1875. And in this article, he basically studies different structures of the form, so N carbon atoms, 2N+1 hydrogen, and then this extra OH at the end. And so he goes through different values of N. So when N is 2, for instance, you'd have 2 carbons and 5 hydrogen and this extra OH. And he goes through and he counts the different kinds of graph structures you could have with this carbon and this hydrogen and the extra OH. And he goes through and he figures out that, okay, when N is 1, you get 1. When N is 2, you get 1, 2, and 4. And so these match the known chemical compounds at this time in 1875. So there's this apparently this famous book, Carbon Compounds, 1874, that he cites. And so the number of chemicals, molecules of this type match what you know from the different types of graphs. But the interesting thing is that when N is equal to 5, there were only 2 molecules of this type known, but he computed that theoretically there are 8 different graphs that you can make that are not equivalent with this. And so then he says, of course, there could just be more in theory that there are actually in the world, but maybe the missing ones are simply unknown. And indeed, I don't really know very much chemistry, but when I was doing some background on this related to one of my research projects, I looked this up, and it turns out that yes, indeed, there are 8. So these are known as pentanol now, when N is equal to 5. And there are 8 different what are known as isomers of pentanol in modern times. So by studying this discrete structure, this graph with certain properties, so how many vertices each vertex is connected with, he was able to essentially see into the future and realize that there are more structures that were waiting to be discovered. Something that I am very fond of is this notion of a lattice walk. So a queue, sort of a system where people line up and get served, can be modeled by this discrete structure of a lattice walk. So let's suppose I have a very simple queue. I have a bank, and there's 2 tellers at the bank, and people will come in and line up at the tellers, and then they'll get served by the tellers and leave. And so, let's suppose someone comes in and goes to teller number 1. I can model this by looking at what's known as a walk in the plane by increasing by 1 on the x-axis anytime someone enters line 1. And if someone enters line 2, then I can increase in the y-axis. And maybe banks are pretty slow, so maybe someone else joins before they join line 1 before anyone else has been finished being served. And so then you go over for the first person, up for the second person, and over for the third person. And now let's say this person just had a quick, they're depositing some money or something, so they have been served. Then we can decrease this to say that there's no one waiting in this line anymore, and then maybe someone's processed from line 1 and the last person's processed here. So this is an example of a lattice walk. We're essentially modeling how people enter and leave these lines by moving north, south, east, west in the plane. So we can think of this as a sequence of these steps. And there's an interesting constraint here, which is that you can never have negative people in line, right? It doesn't matter if everyone has been served, you can't serve anyone else. So in terms of our walk is restricted to the first quadrant here. And then you could ask yourself different properties. You could ask yourself, what properties these kinds of walks have. What's the chance that you would stay in the first quadrant? So you're actually modeling this queue. More generally, you could have more advanced setups with different tellers or sub-tellers for a super teller, and you could say, how efficient do we expect these different queue systems to be? Again, I'm giving some kind of smaller examples here to help illustrate the theory, but in general, these are applied in computer science to routing on the internet or something like that. So you have like thousands or hundreds of thousands or millions of queries that are being processed or put into queues and things like that. So everything I'm talking about, I'm using usually small scale to bring it up, but really you want to know how these things behave at very large scale. And so here, for example, is a bunch of lattice walks. So if I take 400 lattice walks and I just run them moving north, south, east, west, and I look how many stay in the first quadrant, then after 300 steps, only one of my 400 walks stays in the first quadrant. So you could say, okay, is that realistic or not? And you can also use this to model with a small modification, what is the chance that no line is empty in the whole time that the queue is going on, things like that. Right? So we want to study properties of these queues, and to do that, we can study this mathematical structure of lattice walk. Something that I personally, I really like lattice walks. I'll mention them again later. Some of my first work I ever did when I came to Paris was to work with Aline, actually, the moderator of this, on lattice walks. So I have a soft spot for lattice walks. I think they're very interesting, and they also provide great models for coming up with new tools to study this, to study many different problems mathematically. Now, a lot of what I'm going to be talking about today was actually developed in computer science, and in particular, theoretical computer science. So in theoretical computer science, your main object of study usually is an algorithm or a sequence of steps that solves some problem. So I'll just give a quick example here. One of the more famous examples of an algorithm that you'd see in a first computer science course, either in high school or when you go to university, would be this quicksort algorithm. So quicksort, it takes in a finite list of distinct numbers, and it outputs a list of the numbers in increasing order. So it sorts them in increasing order. And the way quicksort works is fairly simple. So let's suppose I have this list 6, 1, 3, 4, 5, 2. So of course I want to sort this. I want to get 1, 2, 3, 4, 5, 6 in the end. So first, let's say step 0. If my list only has one number, I just don't do anything, right? Because it's already sorted. It's only one thing. Now, second of all, what I'm going to do is I'm going to pick a random element in my list. And so let's suppose I pick the number 4. Okay. Now I divide my list into the elements that are smaller than the number I picked, in this case 4, and those that are larger than 4. So in this case, okay, I'll put my number 4 down here, and then I go one by one and I say, oh, 6 is larger than 4, so I'm going to put it to the right of 4. And then 1 is smaller than 4, so I'll put 1 to the left of 4. Then 3 is smaller than 4, so I'll put it to the left. 5 is larger, so I'll put it to the right, and 2 is smaller, so I'll put it to the left. So now 4 is in the right spot because everything to the smaller is to the left and everything bigger is to the right. But I've got these sort of sublists of smaller and bigger things that need to be sorted. So I just repeat the same process on the left and the right. So maybe I now pick 2 on the left and 5 on the right, and then I do the same thing. And now you get, again, in these lists, things that are smaller than 2, bigger than 2, and bigger than 5. And then you would repeat this again, except now all my little lists here, the blue and green, only have one element, so I know that I do nothing. Right? So I started with this arrangement of my numbers, and I end up with them sorted. Now, again, when you're running, say, a sorting algorithm in computer science, often you're dealing with a huge amount of data, like millions of entries. So you want to know how efficient your sorting algorithm is. And again, if you take a first course in computer science at university, you'll learn several different sorting algorithms. And as you go on, probably even more, and all different ways of comparing them and things like that. One of the first ways you'll see to compare sorting algorithms is to count the number of comparisons they do. So you count how many times you compared two numbers when you were doing this algorithm. So in this case, in our first step, we did 5 comparisons because we compared every number here to 4, except for 4 itself. Then in the second step, we did 2 comparisons because we compared everything to 2. And in the final step, then we did 1 comparison because we compared 6 to 5. Okay, and so in total, we did 8 comparisons. And then you could say, okay, is that efficient or not efficient? You could try and compare that to other algorithms. And again, usually with large amounts of data. So for instance, here, what I did is I took, I randomly generated a list with 200 numbers, and I counted how many comparisons it took when I ran quicksort. And then I repeated that 1,000 times, and I took the running average. So if you just sort one random list, it could be really high or really low. But the idea is that if you sort a lot of lists of the same length, then over a long period, the amount of comparison starts to sort of normalize to something here. And so in particular, in this case, you'll see that when I just did my first list of 200 elements, it was a little high, then it got a little low, and then over time it went to this red line here, which is 400 log 200. So on average, the number of comparisons when you run quicksort on a list of 200 numbers is something close to this. And so again, this is a discrete structure. The algorithm itself is a discrete structure, right? It's a sequence of steps, and those steps are kind of the indivisible units. Okay. So this is sort of the end of the intro where I'm talking about discrete structures. These are some motivations for why we want to know different properties of discrete structures. Now we're going to move on and say, how do we actually study discrete structures? And sometimes I'll call discrete structures combinatorial objects. So we're going to study the behavior of combinatorial objects using sequences. A sequence is just a list of numbers, right? So if I have a sequence A sub n, I'll say I have A0, A1, A2. The number in the bottom here is called the index of the sequence often. And I would always start with index 0. Some people like to start with index 1. For me and for a lot of computer scientists, it makes sense to start with index 0 here. Now, for most of what I'm going to be talking about, we're going to be counting various things. So usually these numbers in my sequence are going to be natural numbers, but they don't have to be. In fact, pretty much everything I'm going to say will work for complex numbers. And much of what I'll say will actually work for even more complicated things like numbers in finite fields and things like that. Just as an example, if I have the sequence, say A sub n is 2 to the n, then the sequence, when n is equal to 0, you get the number 1. When n is equal to 1, you get the number 2. When n is 2, you get the number 4, and so on and so on. Okay. So sequences will somehow encode something about our objects, and that'll allow us to study these objects. And so, sequences, if I have a discrete structure, a discrete object, the sequence could do a lot of different things. So one thing it could do is count the number of objects of a certain kind. So for instance, I could say that Cn is a sequence that counts the number of ways to make change for n dollars using pennies, nickels, dimes, and quarters. And maybe for people in different countries, so pennies are worth 1 cent or 1/100th of a dollar, nickels are 5 cents, dimes are 10 cents, and quarters are 25 cents. My sequence could capture the probability that something occurs. So maybe P sub n would be the probability that two randomly chosen numbers in the set of numbers from 1 up to n are coprime. Now here you see an example where you probably would have something that's not a natural number, right? It would probably be a rational number because you're talking about a probability. It could also track the runtime of an algorithm. For instance, Q sub n could be the average number of comparisons performed on quicksort when you take all the different arrangements of the numbers from 1 up to n. So we're going to study something about our objects using a sequence. And then our goal is usually to say something interesting about a sequence. Now, this is a very broad goal, right? It's not very precise. So there's a lot of different things you can mean when you say something interesting. I'll go through a few of them. Now, one thing that you could mean is an exact formula. So here's a very famous example. I didn't mean to have so much from Kaylee, but this just happened to come up. So this is a formula that was popularized by Kaylee for something known as labeled trees. So you can think of this as different networks like the internet, except there are no cycles. So you can never start at a website, go to another website, go to another website, and then eventually get back to one of the websites you visited before. Okay, so if you look at these types of graphs, these are known as trees, and it's long been known that you have this extremely nice formula, n plus 1 to the n minus 1 for the number of labeled trees on n vertices. So in the internet, this would be you had n websites. Very beautiful result. You prove it in many kinds of combinatorics courses using different methods, and it's very beautiful. But it's unreasonable to expect that every possible question you could have would have such a nice form in the end. Not all combinatorial sequences have nice forms. Some have very complicated forms. Some might not even have really efficient forms at all to compute. And even if you have a problem that does have a nice form, it can often be very hard to prove a nice formula for it. So exact formulas can be nice, but it's kind of too naive to expect that you can always get them. Something else you can ask for is an efficient algorithm. So a sequence that many people here might be familiar with are the Virahanka-Fibonacci numbers, usually often called the Fibonacci sequence. So this is what is known as a recursively defined sequence. So you start by saying the first two values are 1, and then to get the next value in the sequence, you add the previous 2. So for instance, you start with 1 and 1, and then 1 plus 1 is 2, so the next number is 2, and so on. And so this sequence was studied in India and other places, in a long time ago, and it was popularized when Fibonacci Leonardo da Pisa put it in his book Liber Abaci in the 13th century. And here you see a copy of the Liber Abaci from the 14th century, and you see on the right-hand side there, you have the numbers of the Fibonacci sequence. Okay, so this is one way of defining the sequence, but what I want to talk about here is an algorithm for computing terms of the sequence. Now, I don't want to get too much into it, but it turns out that this small piece of code here, 10 lines, including some extra white space and things like that, this computes the Fibonacci numbers very efficiently. And this is code in Sage. I believe one of the other courses here is talking about Sage. So if you, after you take that course, you can look at this code and see if you can figure out what's going on. It does use a little bit of linear algebra. But the point I want to make here is just that if you believe me that this code computes the Fibonacci numbers, if you see here, there's this command fib 10 to the 6. So this is saying we're computing the 1/1,000,000th Fibonacci number. And what the output says here is that I can do that in 10 milliseconds. So almost instantly, I can compute the millionth Fibonacci number. And this is over 200,000 digits long. So in a sense, if you want any Fibonacci number that you actually can look at and understand, because you already, of course, cannot understand a number truly that's 200,000 digits long, you can get it basically instantly with your computer using this code. So in a sense, that is saying something interesting about the sequence. It's telling you, here's a way to compute any of the numbers you actually would probably care about. Of course, gathering data can be very useful for studying sequences. Maybe you can conjecture some formulas, but it doesn't fully capture the behavior of what's actually happening. So this brings me to the last thing I'll talk about right now, which are asymptotics. So instead of counting something exactly, which can be very complicated, instead we could focus on the large-scale behavior of a sequence by approximating the terms in our sequence when the index n is very large. So if I have a sequence f of n, I'll say that it's asymptotic to another sequence g of n if the ratio f of n over g of n goes to 1 when n gets larger and larger. And the idea is that we're going to ignore terms that don't make much difference in our sequence that could be very complicated to simplify results. So for instance, here you see two plots. One is n squared plus n plus sine log of n, and the other is just n squared. And you see here that the two functions stay very close together. And in particular, when n gets large, they differ, but the amount they differ by is very small compared to how big they are. So the sequence on the left, you have this extra n term, you have sine of log of n. Sine of log of n is kind of complicated to figure out, but of course it's always between -1 and 1. So if you're dealing with numbers that are millions or billions large, who cares if you have plus or minus 1 to your sequence, right? Overall, you can just kind of ignore that, relatively speaking. So asymptotics are a way of giving a good approximation and giving really clean results that help you study the behavior of your sequence and therefore your discrete structure without getting too bogged down in the nitty-gritty details. So for instance, the average cost to run quicksort on a random list of n numbers, so the average number of comparisons, turns out is asymptotic to 2n log n. So this explains this sort of behavior where you're approaching the red line in the graph I showed before. If you want to count the number of graphs on n nodes or n vertices, it turns out that there's a nice argument that's been known for decades that this is it's a very large number. So you have 2 to the 2n choose n, for those who know what a binomial coefficient is. If you don't know, that's okay. Just know that this is a very big number that you can compute explicitly, divided by n factorial. N factorial is also a big number, but this is a even much bigger number. And the thing I want to point out here is that it's actually been an open problem for at least 40 years, whether the number of graphs on n nodes can be computed in polynomial time. So forget about finding an exact formula, right? This is even just saying, can you find an algorithm that computes it in a reasonable time? And it's unknown if that exists. Now, the final thing I want to talk about before we go on to talking about how we can prove or find some of these things is something that's a little bit more advanced, which are limit theorems. So in order to capture the large-scale behavior of parameters of an object, so not just the number of objects of a given, or not just track one thing like the number of comparisons, maybe you want to track multiple things, then we can use multivariate sequences, and we often can derive what are known as limit theorems. So I don't want to get too much into this, it's more advanced. Most of my research these days is working with multivariate sequences and finding their asymptotics and limit theorems and things like that, but it's a little too much to go into in this talk. If you're interested, as Aline said, I recently wrote a a book about the topic. Actually, I've written 2 books about the topic in the last several years. So there's lots of places for you to consult if you're interested in. But for now, I just want to give 2 quick examples. So I'll start with an example of what's called a composition. So a composition is sort of a combinatorial or mathematical structure. It's so a composition of size n is an ordered list of positive integers that add to n. So for example, the compositions of size 3, you could just have 3 itself. You could have 1 plus 1 plus 1. You could have 1 plus 2. You could have 2 plus 1. And because we're considering an ordered list of positive integers, we treat 1 plus 2 and 2 plus 1 as 2 distinct things. And it turns out, we'll see later how to prove this actually, if Cn is the number of compositions of size n, then Cn is 2 to the n minus 1. So there are 2 to the n minus 1 compositions of size n, as long as n is bigger than or equal to 1. That's a very nice result. Again, we'll see a slick way of proving this near the end of the talk. But what I want to focus on now is, what if I don't just care about the size of a composition? What if I also want to keep track of how many ones it has? So now I'm tracking 2 pieces of information: the size, or the sum of the list of positive integers, and the number of times 1 appears. Now, if you plot out, let's say, the compositions of size 200 by the number of ones they contain, you get something that looks like this. Of course, this is sort of a normal curve looking thing here. And so this is an example of the limit theorem. So limit theorem would say that as the size of the compositions gets larger and larger as it goes to infinity, if you track the number of ones, you approach a certain shape, and in this case, a normal distribution that you might know from other contexts. Again, these kinds of results are very powerful. They appear in many different places. So if you look at theoretical computer science, actually, there's a lot of interesting limit theorems that appear. For instance, some of you may know the Euclidean algorithm, which is an algorithm for computing the greatest common divisor of numbers or polynomials. And if you run the Euclidean algorithm on random pairs of polynomials, and you track how many divisions you do when you compute this GCD, and in this case, I'm working with polynomials whose coefficients are reduced to always lie in 0, 1, or 2. If you keep taking more and more, if you run the Euclidean algorithm on more and more pairs of polynomials, then you'll see that over time, you actually scale to something that also looks like a normal distribution. So these limit theorems, they're cool and interesting, but they also tell you something about the computation or the cost of running the Euclidean algorithm and what it looks like in the long run. Okay, so that finishes part 1, sort of the setup, why we're interested in discrete structures, the basics of sequences, and what we want to find for sequences. Now we're going to start talking about how we can actually say something interesting about sequences. Now, for me, I'm sort of on the border between mathematics and computer science. In fact, at the University of Waterloo, I'm in a department of combinatorics and optimization. So I'm not in a math department or a computer science department. I'm in a combinatorics department, which is something fairly special to Waterloo. And so I'm always interested in methods of computing things. So even if I'm looking at mathematical objects like sequences or just numbers, I want a way of automatically manipulating them on my computer. And so we're going to talk about how we can encode sequences and manipulate them. But before we get to that, I want to start just by thinking about mathematical objects like numbers. So forget about sequences. We're just going to say, how do we encode a number on my computer in a way that I can manipulate it and say something interesting about it? So if I have an integer, or let's just say a natural number, it's fairly easy. We can just store it using a binary representation in my computer's memory. And okay, there's an infinite number of numbers and my computer memory is finite, but aside from that technicality, if I kept adding more and more memory, I could store any integer I wanted to. Right? If I have a rational number is a pair of integers. So I can store a rational number as its numerator and denominator, and then each of these I can encode in binary. And if I want to add rational numbers or multiply them, then I can manipulate these pairs of integers and update and do everything I need to. Now, something that's more interesting is to look at the set of algebraic numbers. So these are the roots of polynomials with integer coefficients. Now, here we can store algebraic numbers implicitly. So instead of storing it exactly or sort of explicitly, for instance, using binary representation, we store it implicitly using a polynomial that it's a root of and some extra information. So for instance, if I want to store the number square root of 2, then I can say it's a root of the polynomial x squared minus 2, and x is bigger than 0. And both of these pieces of information is necessary. So x squared minus 2 tells me it's one of two numbers. It's either root 2 or negative root 2. And then saying that x is bigger than 0 tells me it's positive root 2. And of course, an integer polynomial I can store exactly, because that's basically a list of integers given by the coefficients. And I can store each of those integers in binary representation. And the extra bit of numeric information, you can come up with different ways of showing this using inequalities or things like that in terms of integers and rational numbers. Okay. Now, I just want to spend a second talking about this encoding of algebraic numbers, because there are algebraic numbers that cannot be represented exactly. So for instance, if you look at this polynomial here, y to the 5 minus 4y squared plus 1, this is what's known as not being solved in radicals. Now, to fully understand this or to prove this, you'd usually take a course in Galois theory later on in a mathematical career in undergrad or grad school. That's not important now. I will mention that there's a way to do this automatically. So if you go into Sage and you run this code here, the fact that it outputs false shows that this is not solvable in radicals. And what that means is that there's no explicit representation in terms of things like square roots or cube roots or fourth roots or fifth roots. Okay, so you can't really write down exactly using just integers what the roots are here, at least in a systematic way that you could do for other polynomials too. And so our representation of algebraic numbers is implicit, right? We can talk about the roots by using this polynomial they satisfy and some extra information without actually going and writing them down explicitly what they are. And now this is, in general, when you're thinking about manipulating numbers, you have to be very careful. So there's, here's a very beautiful result. One of the most beautiful results, I think, in computational mathematics. It's a kind of a combination of results. So it's often called the MDPR theorem for a bunch of people who worked on intermediate results that led up to this. But what it says is that if you give me, there's no algorithm that takes an arbitrary expression that's composed of a constant 1, addition, subtraction, multiplication, sign, absolute value, and a single real variable x, and tests whether the expression is equivalent to 0. So it's an undecidable problem. There is no algorithm that can test equivalence to 0 for these types of expressions. And that's kind of crazy, right? Because the simplest thing you could ask to do computationally with an expression is just say, is it equal to 0? So in general, what this means is that things can be quite bad, of course. And then we're not even using division here, so you don't have to worry about dividing by 0. But you know, in general, things are not so bad. For instance, it turns out for algebraic numbers, you can compute effectively. You can decide equalities between them exactly, and things like that. And the key is you need to use tools from mathematics. So in particular, tools from commutative algebra, things like resultants, which most of you probably have not heard of before, but if you go on and take more courses in mathematics, you will learn about them and you will see how you can compute with these algebraic numbers. I had a really nice example that illustrated how you could prove some kind of interesting equalities using resultants, but I had to cut it due to time. The slides here are available on my website, and maybe the organizers also make them available. But if you look in the slides when they're posted after the end of the slides that I get through here, there are some bonus slides, and in there it has this interesting example. So you can look for that if you find this kind of thing interesting. Okay, so that's talking about encoding numbers. Let's get back to encoding sequences, right? So basically, I have some discrete structure. I want to study something about it. So I create a sequence that tells me something interesting. And now I want to encode this sequence in a way on my computer, let's say, so that I can manipulate it or get some extra information about it. Now, one way to do that would just be to have an explicit expression, right? So say that the nth term of my sequence is 2 to the n. So that would be a way of writing it down. But again, that's a little too hopeful. There might not always be a nice explicit expression. It might not be easy to find. Something else you could do is find a recurrence. So recurrences are very useful. Of course, recurrences don't always exist either. But even when they do exist, it can sometimes be hard to see the behavior of your sequence from a recurrence. So if we go back to these Virahonka Fibonacci numbers here, it's a very beautiful definition, very interesting sequence. Some of you might have seen before that there's actually a way to write down an explicit formula for the sequence, and then from this explicit formula, you can also find asymptotics. If you just want to know, for instance, roughly how large the millionth Fibonacci number is, it's much easier to use this formula than it is to use the recursion. And of course, recursions can be more and more complicated as well. So recurrences can also be useful. Everything I'm talking about here, I don't want to give the impression that it's not useful. Every way of encoding a sequence is useful in certain contexts. But in general, recurrences, they have some upsides, but they also have some downsides. So what I want to focus on here is something that many of you maybe have not seen before. It's this notion of a generating function. So generating function is the basis of many powerful methods. I only have a little less than an hour left in my talk, but I hope to give you many examples to show sort of how beautiful these beautiful results you can get using generating functions, how powerful they can be. And the definition of a generating function is fairly simple. So a generating function of a sequence, it's a series, so an infinite sum in a variable. Usually I use the variable z, but of course you could use different variables too, where the coefficient of z to the n, so the number in front of z to the n, is just the nth term of your sequence. So you'd get f of 0 plus f1z plus f2z squared, and so on. So one of the key things to take away from this talk is that generating functions form data structures for sequences. So for instance, the generating function of the sequence f of n is 2 to the n. So it's 1 plus 2z plus 4z squared plus 8z cubed, etc. It turns out this is equal to a very nice rational function, 1 over 1 minus 2z. Now, why is this true? So there's a few reasons here. So first of all, this holds actually algebraically. So what does it mean if this infinite series is equal to 1 over 1 minus 2z? Well, what that means is that if I take that infinite series and I multiply by 1 minus 2z, I should get 1. And indeed, if you take this here and you expand it out, then when I take the infinite series and I multiply by 1, I get the infinite series back. When I take that infinite series and multiply by a negative 2z, I get basically the same thing, but shifted over with a negative sign in front. And when you add them up, then you just get 1. So this is showing algebraically that this infinite series, this generating function, is this rational function, 1 over 1 minus 2z. Now, there's a whole algebraic theory of generating functions, what are known as formal power series. It's very beautiful, and you can show a lot of interesting things with some algebra. I don't have time to get into that today, so I'm just sort of going to give some examples and wave my hands a little bit about the formal theory, but this argument that I presented here basically works in a formal way if you give the right kind of background to it. But not only does this hold algebraically, this actually holds as functions if you put in numbers whose absolute value is less than 1/2 for real numbers, or whose modulus is less than 1/2 for complex numbers, for those of you who are comfortable with complex numbers. And that holds, for instance, by Taylor's theorem from calculus. So for instance, if you set z is equal to 1/4, then you'd get the identity that 1 plus 1/2 plus 1/4 plus 1/8 and so on is equal to 2. So this holds algebraically, and it also, in this case, holds as a function. Okay, so generating functions will allow us to encode these sequences, but we're not interested just in sequences. We're usually interested in some kind of objects, right? And then we model them with sequences. So we just need one more definition to get us going here. That's the definition of a combinatorial class. So a combinatorial class is sort of what we're going to study using generating functions, and it's composed of two things. So first, it's composed of a set of objects. So that's just a set of things. Usually it's going to be infinite. It could be finite too. And we want to count objects using sequences. So we need a way of saying how large they are or somehow distinguishing them. So we have what's called a weight or a size function, which takes an object in our class and returns its size. Usually we use the absolute value bars for the size. And this will just be a natural number. So 0, 1, 2, and so on. And since we're going to be counting things, we need to know that there are a finite number of objects, of elements in the class of any size. Right? I don't want to be counting things and then say that there are an infinity number of objects of size 2. That's not good for counting. Right? I don't want to have any infinities here. So I want my set of objects, my whole set of objects could be infinite, but if I look at those of any size, I need that to be finite. So as an example, we could look at the set of what are known as binary strings. So these are basically all the ways that you could write zeros and ones in a finite sequence. Or another way of saying it is it's just the natural numbers when you write them in binary. Except I also add this extra thing at the beginning, this epsilon, which I call the empty string. This is like just having an empty space. So it's something that has size 0. And this just is usually thrown in because it helps sort certain definitions of manipulating binary strings. So if I take the set of binary strings, this is my set of objects, and I also need a size function. In this case, probably the most natural size function is just the length of the binary string. And that is a combinatorial class, because if you look at the number of objects of any fixed length, then you only have a finite number of binary strings. Now, a non-example would be if you take the set of binary strings, but you take the size to be the number of zeros in the string. Now, this is not a combinatorial class because, for instance, the empty string and the string 1 and the string 1, 1 and the string 1, 1, 1, these would all have the same size. They'd all have size 0 under this new definition because they don't have any zeros in there. Okay, so combinatorial classes are what we're going to be studying. Now, if I have a combinatorial class, I'm going to define the counting sequence of my class to be the sequence C of n, where C of n is the number of objects that have size n. And the generating function is then the generating function of the counting sequence. So it's a infinite series in the variable z, where the coefficient of z to the n is the number of objects of size n. So for instance, if I look at the generating function for the class of binary strings with size given by length that we saw in the last slide, then the generating function, well, there's a single object of size 0, which is the empty string, so we have a 1 in the front. Then there are 2 objects of size 1, just 0 and just 1. There are 4 objects of size 2, 8 objects of size 3, and so on. So I get this series, and we already saw that that's this rational function. So I can encode something about the class of binary strings, how many there are at a given length, by this rational function. And again, one of the key takeaways from this talk, perhaps the key takeaway, is that generating functions give an algebraic encoding of a sequence. It's a way of writing down a sequence in a way that you can manipulate using mathematical tools. Right? They allow us to apply tools from pure math. Before we go on, I just want to mention there's also an alternate definition of the generating function, which is instead of summing over all the sizes, you sum over all the objects in your class, and you take your variable z, and the exponent is the size of the object. Because let's say you had 5 objects of size 2, then in this sum, when you sum over all the objects, you get a z squared 5 times. So there's 2 different ways you can write this down, and each is different, is useful in a different context. Okay, so that was a decent amount of definitions in a row. So I think we had this example of binary strings, but let's see some more interesting examples that already start to show the use of generating functions. So I'm going to start with one that I think is pretty fun, which is looking at dice rolls. So first of all, let's say, what are the generating function of different rolls of a dice, where the size of a roll is the number of dots that appears. So it's the size of, it's the number that's on the top of the dice. So if I take a dice and I see all the different ways I can roll it, all the sides, of course you get 1, 2, 3, 4, 5, 6. So the generating function here, well, I have one object of size 1, which is this face. I have one object of size 2, which is the second face, one object of size 3, which is the third face, and so on and so on. And okay, so that's kind of interesting, I guess. It doesn't really say that much though. But here's where the interesting thing is. Let's look at the generating function of pairs of dice rolls. So all the ways that I could roll 2 dice together. And so it turns out that, well, for instance, I could have a 1 and a 1 appearing, and that would give me something of size 2. And that's the only way to get a 2. So I have z squared. There are 2 ways to roll 3 with a pair of dice, because you could get a 1 and a 2 or a 2 and a 1. There are 3 ways to roll a 4, and so on and so on. Something that we'll get back to later, this is actually the generating function of a single dice roll squared. And that's a hint at a more general phenomenon that we'll talk about later. Now, what I want to ask is this interesting question. Is there a pair of distinct dice? So different dice, now you have different numbers on the sides, but they're still positive integers. And you can have repeated sides, and they can be larger than 6. But the dice are different. And the chance that you roll any number when you roll this pair of dice is the same as the chance you get that number when you roll a standard pair of dice. So it's an interesting question. You can think about it. Generating functions actually turns out to give a really beautiful way of solving this, to answering this question. So if you think about it, the new pair of dice, it has the same chance of rolling each number. So it still has the same generating function. Now this generating function is a polynomial. So we can apply tools from mathematics, right? We can factor this polynomial, and if you factor it, you get this. Of course, every term here is squared because we saw before that this polynomial is a perfect square. And here's the cool thing, is we can move these factors around in a way that looks like this. And if you do that and you expand, then you get the product of two polynomials whose exponents are positive integers and whose coefficients are natural numbers. And in particular, this gives you a new set of dice, which are known as Schumann dice, whose chance of rolling each number is the same as the standard pair of dice. So for instance, this term here, the first one, there's a Z, so that means there's one object of size 1, so there's one face with one dot on it. There's two objects of size 2, so there's two faces with two dots on them, two faces with 3 on them, and one face with 4 on them. So that's kind of cool. In fact, if you put a little bit more work in, then you can figure out, you can show that this is the only set of dice that are distinct and have positive integer sides that have the same probability as the standard dice. So not only is this one of them, this is the only way to do it. And again, the key thing I want to get out from this example is that, okay, there's this cool thing that you could, buy these dice online and then show your friends, oh, it actually is the same as regular dice. But aside from that little cool factor, the point of this example is that generating functions allowed us to use mathematical methods, in this case, polynomial factorization, to say something about combinatorial objects in dice rolling, right? So we could study things related to dice rolling using mathematics. And that's very cool, and that's kind of the heart about what enumerative combinatorics is. It's taking results developed in mathematics, sometimes 100 years ago, sometimes 5 years ago, sometimes you develop them yourself when you're interested in a certain problem, and applying it to different applications of combinatorial objects or structures that model the internet or genes or all these different things. Okay, so that's the end of the first first main example. Let's look at another example, which is also a very famous example and is a very cool example, I think. So this goes back to something we saw before. Let's try and figure out how many ways you can make change for $1 using pennies, nickels, dimes, and quarters. And again, for those who are not used to this terminology, pennies are 1 cent, so 1/100th of a dollar. Nickels are 5 cents, dimes are 10 cents, and quarters are 25 cents. Now, in order to solve this problem, we're going to make a combinatorial class that encodes the number of pennies, nickels, dimes, and quarters you could have. So we're going to have a combinatorial class whose objects are tuples of 4 natural numbers, A, B, C, D. So A will be the number of pennies, B is the number of nickels, C is the number of dimes, and D is the number of quarters. And the size of my tuple will be A plus 5B plus 10C plus 25D, because that means the size of a tuple is how many cents it makes. Right? Cn, then the number of objects in my class of size n is the number of ways that I can make change for n cents. Now, if I look at the generating function by definition, by the second definition of a generating function, you can sum up over all objects in your class, all these tuples, z to the size. Now we know the size is just this. Now here I'm going to use a little bit of algebra. If you're familiar with infinite series, this should be straightforward for you. If you're not, then maybe you can just believe this step. But it turns out that this infinite series here is the product of 4 individual series. And the reason this is true, for those who haven't seen it before, basically if you just expand out each term, then you can, in this product, then you can get the series from the first one. Now, as we basically saw before, if you sum up the powers, so y to the n, you get a rational function, 1 over 1 minus y. We saw this before where y was equal to 2z, but it's true just for y for the same reason. So what that means is that if I have my generating function here, then the first series is just basically the same thing. I just set y is equal to z, and I get a 1 over 1 minus z. The second term in the product is basically the same thing, but I set y is equal to z to the power of 5. So I get a 1 minus z to the 5 in the denominator of my rational function. Then I set y is equal to z to the 10, y is equal to z to the 25. So the generating function of this combinatorial class is this rational function. And again, this encodes how many ways I can make change for n cents. So my question was, how many ways can I make change for $1? How many ways can I make change for 100 cents? You can go into, for instance, Sage and ask it to compute the terms in this series. So for those of you who know Taylor series, you know that you can compute this by taking derivatives. That is by not even close to the most efficient way to do it. There's lots of interesting techniques in computer algebra that are used to compute coefficients in series, for instance, in rational functions, when you expand them as series very efficiently. But you can go into Sage, anyway, in this case, and just ask it to run its series command, and it will easily give you the first 100 terms. And when you do that, you see that you get this 242 times x to the 100. And so this means that there are 242 ways to make change for $1 using pennies, nickels, dimes, and quarters. And again, we use generating functions to give an algebraic structure. We simplified the generating function and then computed this series. And this also shows that computational tools are very useful. And when you have these encodings of generating functions, then you can use your computer to do some brute force and help you with your problem as well. Okay, so I want to end with a family of examples. And the point I want to get across here is that generating functions, again, are a way of storing sequences. And one of the cool things is that the different kinds of equations that your generating function satisfies can be different ways of encoding different types of sequences. So for instance, if your generating function is rational, you can just write it down. Maybe it's algebraic, so it satisfies a polynomial equation. Then you could use this algebraic equation to encode it, sort of like we saw for square root of 2 for numbers. Maybe it doesn't satisfy an algebraic equation, but it satisfies a differential equation, which you might have seen if you've taken a course in calculus. Then you can use this differential equation to store your sequence, and so on and so on. And so you can use different types of equations for generating functions to store the generating function, which then stores the sequence. And you could ask about what kind of properties of your sequence or about the discrete structure you can get from these different types of encodings. So just to quickly go through some examples here, I'm not going to show how you get the generating functions here, except in the first case. So if I'm looking for the number of walks that start at the origin, and they take n steps in north, south, east, west, kind of like we saw before for queues, but I'm not restricting myself in any way right now, then, okay, we say by convention there's a single walk of length 0. There's 4 walks of length 1, because I have 4 steps, I don't have any restrictions, so I can move, in any of the 4 ways. There are 16 walks of length 2, because I took 4 directions at the beginning, then 4 directions again later, and 64, etc. So the generating function, for reasons we've seen before, is just a rational function 1 over 1 minus 4z. Now let's suppose I have the same problem, but I stay at a half space, so I'm never allowed to move to something that has a negative y value. It turns out, using different techniques, one of them, for instance, called the kernel method, which is a method of deriving generating functions for these type of problems, has been developed over a couple decades. You can get the generating function in this case to be this algebraic function. So it's not rational, it has a square root in it, but you can still write it down explicitly. Now, what about if instead of staying in a half space, I stay in what I'll call a 3 pi over 4 wedge, so this sort of shaded region here. Now it turns out that it's still algebraic, but the generating function satisfies this kind of polynomial equation of degree 8. So you cannot write down what the solution is explicitly. You can only encode it using this higher degree algebraic equation. And so again, we can still say something interesting about the sequence. I'm going to talk about it a little bit later. I don't have too much time to get into how you do all these things, but you could try and do exact enumeration, or in this case, what I would try and do is to find asymptotics. So using techniques to find asymptotics directly from this algebraic representation. But the idea is you could find interesting information about your sequence and therefore about the discrete structure without actually getting an explicit representation, but working implicitly with this data structure, which is an algebraic equation. And finally, if we go back to the actual example we saw when we looked at these queues, this example with the 2 bank tellers. So we're looking at walks on north, south, east, west that stay in the first quadrant. It turns out that this does not satisfy an algebraic equation. It's actually an interesting question how you can show that a generating function does not satisfy an algebraic equation. This is related to results in, say, number theory, where you're trying to show that numbers are not algebraic. You can try and use similar techniques to that, but also much more advanced techniques that you don't normally have available for numbers, or let's say more convenient techniques you don't have available when you're studying numbers. So you can show that it's not algebraic, but in this case, it satisfies a differential equation. It's actually a linear differential equation. So you have higher order derivatives, but you don't have like f prime times f double prime or something like that. And you have polynomial coefficients. So this is an example of what's known as a deep finite equation. Okay, so so we've seen some examples of generating functions. These are going to be your main structure. Of course, the natural question is, how do we actually compute generating functions? And so for that, I'm going to talk about what I'll call the symbolic method. Now, there are many methods for computing generating functions. Many of them have a lot of overlap. So I'm going to talk about this one way of presenting these methods called the symbolic method. This method, or this packaging of the method, was, I believe, popularized by this fantastic book called Analytic Combinatorics by Philippe Flageolet and Bob Sedgwick. Highly recommended if you're interested in these kinds of things. And they develop a very beautiful theory, a lot of which I'm talking about today. So the idea is that we're going to look at our combinatorial classes, and we're going to build a sort of calculus of combinatorial classes. We're going to build a way of manipulating them and building generating functions. So the idea is that we're going to start with two base classes, what I'll call the atomic class and the neutral class. So the atomic class, I'll call it script Z here. It's it's a class that has one object of size 1 and nothing else. And so the generating function of this class is just Z, because it's one object of size 1, no objects of any other size. And then there's the neutral class, which I'll call epsilon, which contains one object of size 0 and no other objects. And so it has generating function 1 because it has a single object of size 0. And what we're going to do is we're going to build up more and more complicated classes from these smaller pieces, basically going down to the atomic class and the neutral class. Sort of like, maybe like building a big structure out of Legos or something. You have these small pieces that you put together in different ways, and you're going to use this to build more complicated objects. And I just want to give a warning before we move on. Don't confuse the neutral class with the empty set. So the empty set is empty. It has nothing in it. The neutral class has something in it, but it has something that has size 0 inside of it. Okay. So to build up our classes, we're going to have 3 different operations that I'm going to talk about now. So there's going to be a bunch of definitions coming up, but after that, I'll give some examples how you can do interesting things with these techniques. So the first thing we're going to do is we're going to define an operation on combinatorial classes that I'll call the sum of the classes. So let's suppose I have 2 classes, A and B, and they have weight functions. The sum of these classes is a new class, which I'll call A plus B. So when I have a class, I need to tell you what the objects are, and I need to tell you what the size function is. So the objects is just it's the union of the objects in A and the objects in B. So you just take all your objects in each one and you put them together. Now, the key here is we're going to take what I'll call the disjoint union. So we really need to treat the objects in A and B as different. So one way to do this is you color all the objects in A red, and you color all the objects in B blue. And so then you can always track how many objects there are, which object came from which original set. And the size function of my new class, well, every object in my big set came from either A or B, and not both, because we're having the disjoint union. And so I could just use the size function from where it came from originally. Okay. So as an example, if I have the atomic class and I add it to itself, then I'll have a new class. Now again, because it's the disjoint union, we consider this to be 2 distinct objects of size 1. Now again, you can often just consider one to be colored red, one to be colored blue. And the generating function here, in this case, now we have 2 objects of size 1, so it's 2z. And there's 2 objects of size 1 and no objects of any other size. And if you want, you can try and prove this yourself. I don't have time to prove this here, but if my class C is A plus B, then it turns out the generating function, you just add them. This is one reason we call it the combinatorial sum. Okay, so that's our first of 3 operations. The second one is called the combinatorial product. So I'll let A and B be, again, combinatorial classes with their various weight functions. So the product is a new class, A cross B. So again, I need to tell you what the objects are and what the size is. So the objects are all pairs, where the first element in the pair came from my first class A, and the second element of the pair came from the second pair B. And I need to tell you what the size is. And so for the size, well, the first object always comes from A, so I can take the size of that from my original class A, and I'll add it to the size of the second element from its class B. And this one when you originally see it, some people might think, oh, why don't you multiply the sizes? But it makes sense to add them. I encourage you to think about it yourself. We'll see an example at the bottom of the slide that also reinforces this. But I just want to say that one very nice result of this definition is that if C is the product of A and B as classes, then the generating functions C is A times B as generating functions. So again, this helps motivate the definition of the product. Now, going back to why this is addition, well, we actually saw this before when we talked about pairs of dice, right? The generating function for a pair of dice was the product of the generating functions of the individual dice. And when you're saying the size of a pair of dice, when you put the dice together, you don't multiply how many are on each, right? You add the dots on your dice. So this is one reason why it's more natural to add the sizes or the weights of your class instead of multiplying them. Now, when we have a product, we can just repeat this over and over again to get powers. So we can, the kth power class is just A times A times A k times. And if you keep applying this lemma, you'll see that the generating function of the kth power is just the kth power of the original generating function. Okay, so these are our first two operations. The final one is the most interesting one. This is known as the sequence operation, combinatorial sequence. So let's suppose I have a combinatorial class, and let's suppose there are no elements of size 0. So there's nothing of size 0, everything is size 1 or greater. The sequence class is, well, one way of writing it down is it's either the neutral class, it's the sum of the neutral class, my original class A, the elements A squared, elements A cubed, and so on and so on. Now, this is one way of writing it down. What it actually is, so the objects are all tuples, right? So A times A are all pairs. So, you have 2 elements in your tuple. A cubed would be all 3 tuples. A4 would be all 4 tuples. Since we're taking the union of all these, it's just all the tuples of all the lengths for my objects. And just like before, the size, to get the size of my tuple, you add the individual sizes. Now, here's something that's very cool that might be really surprising if you haven't seen this before, but which I assume most of you have not. But if you think about it, it actually makes a lot of sense. If C is the sequence of A, then the generating function is 1 over 1 minus A. So again, the first time you see this, you might think, wow, that's really interesting. The reasoning is fairly straightforward. So if I take my sequence, right, this is the definition. Now what happens is generating functions. Well, the neutral class has generating function 1. The class A is generating function AZ. The class A squared has generating function AZ squared, and so on and so on. And we've seen before many times this kind of sum can be represented like this. Now I'm sweeping something under the rug here. This doesn't always hold. It's very crucial that my original class had no objects of size 0. If you have objects of size 0, this definition kind of falls apart and doesn't really make any sense, and you'd have an infinite number of objects of a given size, so you can't even define a combinatorial class. But if you don't have any objects of size 0, then you can define this and everything works out. Okay, so that's our 3 operations. There's a lot of definitions. Now let's go back and study some interesting examples. So let's start back at a good old class of binary strings, one of the nicest, simplest classes to study to make sure you're understanding definitions. So what I'm going to do is I'm going to start by having 2 atomic classes. Now the atomic class is just script Z. Sometimes we put little labels at the bottom just to remind ourselves what they're actually encoding. So here I'll say Z0 and Z1 will be the atomic classes that represent zeros and ones. Then if I take Z0 plus Z1, this is the union of these atoms. So this will be the class that contains a 0 and a 1. Now the class of binary strings is all the tuples of all lengths of zeros and ones. So the class of binary strings is the sequence of Z0 plus Z1. And as generating functions, so sequence means you get 1 over 1 minus, and Z0 and Z1, when you take their sum, you add their generating functions, and each of those are just atomic classes with generating function Z. So you add them up, and then you get 1 over 1 minus 2Z, which we saw before. So nothing too surprising there. Let's see a more interesting example. So let's go back to this example that I mentioned very briefly before when we talked about limit theorems, compositions. So recall that a composition of size n is a tuple of positive integers that add to n. So what we can do is we can define the class of compositions and find the generating function. In fact, since compositions are defined in terms of positive integers, we're going to define both the class of compositions and the class of positive integers. So we're going to start by describing the class of positive integers and its generating function, then use that to find the generating function for the class of compositions. So positive integers, one way of encoding a positive integer is it's all tuples, but you don't have the empty tuple because you don't have 0, right? Positive integers has at least 1. So you can take the sequence of atoms and then add an extra 1 on the beginning. That gives a generating function z over 1 minus z. If you think about it, if you expand this out, this is z plus z squared plus z cubed plus z to the 4 and so on. It makes sense that this is the generating function. You could actually just probably write this down without giving the construction, but I decided to do that so you can think about why that's true if you want. Now, our compositions are all tuples of positive integers, which means that the class of compositions is just the sequence of positive integers. So what that means is that the generating function c of z is 1 over 1 minus the class of positive integers, which is z over 1 minus z. Then you can do some algebra to simplify, and you get 1 minus z over 1 minus 2z. And then you can expand this out if you want. You get 1 over 1 minus 2z minus z over 1 minus 2z. Now we've seen 1 over 1 minus 2z before. This is just the sum of 2 to the n z to the n. And the second term is basically the same thing, but you have this extra factor of z here, which shifts things over. So you can figure out what that is when you expand it as a series. You get this. And then if you work out what happens, you get this right here. And so this is showing you, again, this is the generating function for the number of compositions. So this says that there are 2 to the n minus 1 compositions of size n, whenever n is bigger than or equal to 1. Okay? So again, this shows the power of these tools. You take a complicated class or somewhat complicated class of compositions, you break it down into tuples of positive integers. And you take positive integers, you describe them. So you sort of work down to think simpler and simpler things until you can find the generating function, and then you work back. Okay? I'm going to end with one last example, which is a class of so-called binary trees. If you take a course in computer science, maybe in high school, or certainly in university, you'll see a lot about binary trees. They're a very common data structure in computer science. In particular, a rooted binary tree. So I'll call it an ordered graph. So it's a graph of vertices and edges, but now you have sort of an ordering to your vertices. So we're going to have a vertex, say at the top of our graph, and it will point to vertices below it. Okay? And so a rooted binary tree, it's either empty or it's a root vertex, so the vertex at the top, followed by a left rooted binary tree and a right rooted binary tree. So there's only one binary tree a rooted binary tree of size 1. There's 3 of size 2. There's this many, 1, 2, 3, 4, 5, 6, 7 of size 4, and so on and so on. Oh, sorry, no, actually, that's of course false. It's this many here, 2 rows. Anyways, so you can see here all the different rooted binary trees. And so we can specify the class of rooted binary trees. And the cool thing, the very interesting thing, is that because this definition sort of describes a rooted binary tree in terms of other rooted binary trees, we can use our constructions to describe the class of binary trees in terms of itself. So if I am interested in the class of rooted binary trees, let's say I have one right here. Well, it has if it's not empty, it has a root vertex, right? So there's this root vertex here. Then there's a left rooted binary tree. So that I can think of this as being a product of the root with the left binary tree, and then also the right sub-binary tree. And so this is one way of decomposing my binary tree into smaller binary trees, except it could also be empty. So then there's this disjoint union where it could also just be the empty tree. So we have this definition for the class of binary trees in terms of itself. And if you translate this into generating functions, you actually get an algebraic equation that is satisfied by this generating function. Now, this is just a quadratic equation, so you could apply the quadratic formula, and you'd get that your generating function is one of these two functions here. It turns out if you expand these as series, the top one here, which is the generating function, is very nice. It starts 1 plus z plus 2z squared plus 5z cubed, 14z to the 4, etc. So in particular, there's 14 trees of size 4, which I didn't realize because I forgot that there was on 2 lines on the last slide. The other solution here, it actually doesn't even have a power series expansion. So if you work in a bigger class of series, you can expand this, but you'll see that there's this power of z to the -1 in the front. So it's not a power series. It can't be the generating function. So this one on the top is the generating function. Furthermore, you can use something called Newton's generalized binomial theorem that you'll probably see if you take a course in calculus. And you can expand this out, and then you can actually get the number of rooted binary trees. This is a sequence known as the sequence of Catalan numbers, which comes up all over combinatorics and computer science, many other areas that count huge numbers of objects that you would not think are related to each other. A very important sequence and very important in computer science because of this connection to binary trees and other data structures. Okay, so now we know we want to study discrete structures. We do that using sequences. We use generating functions to encode our sequences, and we can build generating functions using this theory of combinatorial classes and combinatorial constructions. Now, at the end here, I want to talk just a little bit about sort of what you can do at a higher level with some more advanced mathematics. So I'm going to be less explicit now and just give a higher level overview, and then also end by talking about some of the recent applications that have been done in research to show you some of the cool types of problems you can study if you go into this area. Okay, so the final part here, part 4, is a hint of analytic combinatorics. So analytic combinatorics is a way of finding properties of your sequences, in particular asymptotics, usually, using tools from complex analysis, which is a branch of mathematics. And so the techniques that we have from enumeration, so things like the symbolic method that we saw, the kernel method that I briefly mentioned for lattice path enumeration, and other specialized techniques that were developed for counting things in different domains, these give encodings of generating functions. So you can have rational functions, algebraic functions, something called R-diagonals, which is the class I study a lot, which writes a sequence in terms of a multivariate function, usually a multivariate rational function. D-finite functions, which are those that satisfy linear differential equations. D-algebraic functions, which are those that satisfy algebraic differential equations. So you could have like the derivative of f squared in your equation or something like that. And the field of analytic combinatorics uses tools from complex analysis, as I mentioned, to find asymptotics from these encodings, and automatically in many cases. For instance, for rational or algebraic numbers, aside from some very pathological situations, you can almost always automatically compute asymptotics of your sequence directly from, say, an algebraic equation that it satisfies, along with a little bit of extra information saying which root of the algebraic equation is actually your generating function. So very powerful techniques, and again, it really illustrates the beauty of taking things from different domains of pure mathematics and applying them to some kind of concrete combinatorial problems. So as I mentioned, I don't really have time to get too much into the theory here. I only have 10 to 15 minutes left. So I'm just going to give a very brief overview of how analytic combinatorics works. So for most of the sequences, for many sequences that you'd be interested in, they grow like some number to the n, so we call this the exponential growth of the sequence, times something that's sub-exponential, so something that grows slower than an exponential. So it could be like n squared or n or log n, something that doesn't grow as fast as, say, like 2 to the n. And so there are two main principles of analytic combinatorics, and they say that to find the asymptotics of a sequence, you should look at what are known as the singularities of your generating function. And without getting into the definition of singularities, this is something you'll learn about in detail if you take a course in complex analysis at university, usually in like a second or third year math course. So the first principle says that the location of the function's singularities determine the exponential growth of its coefficients. So a singularity, you can really think of a singularity as sort of a point where something goes wrong for your function. So one of the most obvious cases is if you're dividing by 0. So for instance, here, if in the function 1 over 1 minus 2z, when z is equal to a half, then something goes wrong because you're dividing by 0. And the coefficients here are 2 to the n, as we saw. Now, another way you could have a singularity is if you have a 0 inside of a square root. So for the Catalan generating function on the right here, we have the square root of 1 minus 4z. So when z is equal to a quarter, then you're putting a 0 inside the square root, something is going wrong. And you'll see, it turns out that the asymptotic behavior of this coefficients which is the asymptotic behavior of the Catalan numbers, it starts with a 4 to the n, so the exponential growth is 4. So on the left, we have a singularity at z as a half, we get 2 to the n. On the right, we have a singularity at z as a quarter, you get 4 to the n. In general, if you find sort of the singularities that are closest to the origin, that are smallest, and you take the reciprocal, that tells you the exponential growth, assuming everything works out. And the second principle is that the type of singularity you have, sort of the way that something goes wrong in your function, that determines the rest of the asymptotics, or the sub-exponential part. So for instance, if you take 1 over 1 minus 2z squared, so now your singularity is at the same spot, it's still at z is equal to a half, but instead of dividing by 0, you're dividing by 0 and sort of squaring it. So you have a 0 of order 2, sometimes we would say, in the denominator here. And so your exponential growth is still the same because the location is still the same with z is equal to a half. But instead of just being 2 to the n, now it turns out that asymptotically you get 2 to the n times n. So by having an extra power in the denominator, you're changing from a constant to a polynomial, just n. And similarly, if you keep a square root singularity, but you move from z is equal to a quarter to z is equal to a fifth, then your exponential growth will change from 4 to the n to 5 to the n. But the next part, okay, the constant in front will change, but you'll still just get an n to the minus 3 over 2 power there. So again, I don't have time to get into the theory of analytic combinatorics. Very, very beautiful theory. I first learned about it when I was an undergrad, and it sort of blew my mind and made me want to go on and do research mathematics. But just at a high level, there's this connection between properties of the generating function that you can study using tools like from complex analysis and the asymptotics of the sequence. And if you want to study generating functions from these different classes, you can use tools from all different areas of mathematics. So if you want to study rational functions, you can use partial fraction decomposition, polynomial root separation bounds, so saying how close together different roots of a polynomial can be, Newton's binomial theorem, etc. If you want to study algebraic functions, you can use this resultants tool that I mentioned before, polynomial system solvers that have been developed in computer algebra, something called Puceau series, which are ways of expanding algebraic functions, something called homotopy continuation, which is a very interesting computational technique for studying various things related to algebraic numbers and algebraic functions. If you want to look at d-finite functions, so those that satisfy linear differential equations, then you can use singularity analysis of differential equations. You can use something called numeric analytic continuation, which I'll talk about very briefly when I mention applications. Again, I don't expect people have seen almost all of these things here. The point is just that if you want to study different types of problems and different types of discrete structures, then you can use tools from different areas of mathematics. I think that's very cool, very interesting. And it's not only interesting because you get to see cool applications, but it also actually, for me anyways, it helps me learn the underlying theory. Because if I want to learn about singularities of complex functions, okay, that's been studied for a long time, it's kind of interesting. But if I want to study it because I want to find asymptotics of some kind of sorting algorithm in computer science, it really gives me a concrete motivation to understand why these techniques from pure mathematics can be useful. And it turns out that so many techniques from pure mathematics can be applied in these enumerative problems, which is very cool. There's also, I should mention, a lot of interesting problems about what you can actually compute. So for instance, it's an open problem if you can find asymptotics for the sequences with d-finite generating functions. You can, in many cases, basically find asymptotics, but it's not known if you can do it for all d-finite generating functions. And it is known that it's not decidable. There is no algorithm to automatically find asymptotics for generating functions that satisfy algebraic differential equations, d-algebraic generating functions. So it's basically known, again, there are some really pathological cases, but basically known for algebraic generating functions that you can always find asymptotics automatically. It's known that you cannot for d-algebraic functions. And so people are working in between these to say, what exactly can you compute automatically? And can you actually find algorithms to do that? And then maybe make methods that other researchers can use to study different problems. That's what I find very interesting. That's what I spend a lot of my research time doing. So I think I have about 5 to 10 minutes left here. And so I just want to end by going through a few applications of research that I've done. Again, just to show you sort of the types of problems and the breadth of different problems that you can study using these techniques. So the first one, one that I think is very cool, is looking at the structure of biomembranes. So going back a long time now, 1674, this is the first recorded observation of blood vessels. So this guy, Van Loonhoek, basically just took a little bit of his own blood, looked at it under the microscope. He was the first one to ever be able to do that, and he wrote down what he saw. And a little while later, I think about 20 years later, he drew the first picture of a blood cell, which you see here at the bottom. Not very detailed, of course. And the question really is, where does this shape of blood cells come from? Because if a blood cell was a perfect sphere, it would be obvious why it would have that shape, because spheres are very nice. They have lots of nice properties. But as you probably would have seen in high school chemistry class, biology class, cells have this really weird shape, this sort of concave-ish shape. And where does that come from? And not only human cells have this. Canine, for instance, here's a canine cell, has the same shape as human blood vessels. Something I learned when I was doing this project is that all mammals have all healthy mammals, most of them have the same shape of blood cell, except for camels and llamas have a different shape for whatever weird reason, which is not something I thought that I would ever know when I was doing my research, but there you go. Anyway, the point is that this is a pretty universal shape, so where does it come from? And there's a very influential model. It's actually someone who's not too far away from me here in Waterloo, Ontario, someone in London, Ontario, at the University of Western. He developed this model in the 70s for explaining the shape of different biomembranes like blood cells. And so basically what he noticed is that if you deform a blood cell, like you put it through a really little pipette or something like that, then it pops back into this shape. And so that implies something called an energy minimization principle, where there's some kind of function that describes the energy of a shape, and it always wants to get to the lowest energy. So this is kind of a general principle, and he described one model for this. So there's this thing that's been known now as the Canham problem. So this works for a variety of biomembranes. In particular, you fix a genus, which you can think of as a number of holes. So a blood cell would have 0 holes, it would be genus 0. Something like a donut, like that's shown on the screen here, you see there's a single hole, that would be genus 1. You could have 2 holes, genus 2, et cetera, et cetera. And you fix something called the isoperimetric ratio, which is not important, but basically it's something related to the volume and the area of your shape. And he gave a function that you minimize. This is in terms of something called the principal of curvature, which comes from differential geometry. Again, it's not so important. The point is just that there's this function that you want to try and minimize. This function actually has very beautiful history. It goes all the way back to this contest that Napoleon Bonaparte set to describe the shape of certain patterns when you put sand on a vibrating plate, and Sophie Germain entered and kind of was the only one to give a solution that basically derived something related to this, but people didn't really believe it was connected. And anyway, it's a very beautiful, very long history for this kind of function. But for what we're interested in, this predicts, it seems to predict the shape of these biomembranes. In particular, in the genus 1 case, so when you have a single hole, so this is not for blood cells, this is when you have a hole in them. And these biomembranes do occur. For instance, here on the right-hand side, you see something that's actually a picture taken under a microscope. So you do have these biomembranes, but I admit that it's not as important as actual blood cells, genus 0. But in the genus 1 case, there was a really breakthrough result, I think probably about 10 years ago, that proved that you always have a solution for this model. Now, the interesting thing is that it did not prove solution uniqueness. And again, if you have a model that describes the shape of these biomembranes, there seems to be something unique about the shape, right? Like all these different mammals, aside from camels and llamas, have the same shape. So you would expect to have a unique solution for your model. And so before I came to Waterloo, well, a couple of years before I came to Waterloo, I was a postdoc in Philadelphia at the University of Pennsylvania, and across the street is Drexel University. So I gave a talk about enumeration and analytic combinatorics and things that I was working on. And one of the researchers there, Thomas Yu, he came up to me afterwards and told me about this problem and said, I've been able to show uniqueness for this genus 1 biomembrane problem, so when you have a single hole, but I'm stuck on one thing. I have a sequence, so it's a sequence dn, where dn is defined by this, and I can prove uniqueness of the model, but I need to show that all the terms in the sequence are positive. And it might seem crazy that that's related, but it is. Basically, a very high level, if you take the derivative of a certain function, you get a series whose coefficients are the terms in this sequence. And if you show all these terms are positive, you can show the derivative of this function is strictly increasing, and that gives you a unique solution in a certain way. I don't want to get too much into it because I'm running out of time. But basically, to show uniqueness of this problem for biomembranes, you just need to show that this sequence has all positive terms. And that's equivalent to studying the sequence whose generating function satisfies this linear differential equation. So with Marc Mezeroba, who is in Paris, we were able to prove this by adapting techniques from a bunch of different areas: numeric analysis, study of differential equations, and computer algebra. So Marc has worked for a long time on something called numeric analytic continuation. He's an expert at it, and he's developed really amazing software that allows you to basically approximate functions that satisfy certain differential equations up to rigorous error very efficiently, like thousands of decimal places of accuracy. And we were able to use this to find asymptotics with not exact constants in them, but explicit error bounds. So constants that were known up to explicit, basically intervals, and some error in the asymptotics that we can bound. And so we were able to prove positivity, and therefore prove that this model had a unique solution. So again, I'm not really giving the details here. The point is just that we had this application that comes from biology, essentially. And in order to prove something interesting about the biological model, it was reduced to a sequence, and then we applied tools from different areas of mathematics to show something about the sequence. Another application, as I said, I love talking about lattice walks. I've done a lot of work on lattice walks. I think they're an amazing model because you can change different things about your model of walks, like the steps you're allowed to take, where they're allowed to go, write a half space or a quarter plane or whatever. And that gives you generating functions with different behavior, and you can try and figure out new methods for dealing with that. And a lot of tools that have been developed for lattice path problems have been then adapted in many other areas. So some work that I've done here, if you look at walks in an orthant, so not just a quadrant, but in d-dimensional space, if your set of steps is symmetric over every axis, so like north, south, east, west is symmetric over every axis, because if you rotate it over any axis, you get the same set of steps back. It turns out that you can find asymptotics for all these models in any dimension using a more or less explicit formula. Well, it is an explicit formula here on the right-hand side. There are these little S1, S2 up to SD that I didn't write in what those are. Those are just the number of steps that move forward in each coordinate. So this formula is completely explicit. You can look at other lattice path models, like you can look at walks in a quadrant, you can put weights on your model, and then when you vary the weights, you get different kinds of behavior, and you can use this to talk about what are called phase transitions in lattice walks, and how in the models, and how they have different behavior when you put different weights on them and things like this. If you're interested in this topic, the moderator, Aline Bossin, is also an expert at lattice path enumeration. One of the reasons I got into this was working with him a long time ago when I first came to Paris as a research intern with him. And lattice paths appear in many different places. So for instance, here's some work we did that actually looked at different lace patterns. So, lace art is a very old art form. And my co-author here, Veronica Irvine, she is an expert at using mathematics and combinatorics to study lace art, and in particular find new patterns of lace art. So there's different patterns that people use when they create lace, and they basically come from these books that are like hundreds of years old from the Netherlands and other places like that, where people have developed all these patterns that look cool. And she was able to formalize how these patterns are put together and develop new patterns. Actually, developing new patterns is very easy. Developing new patterns that look good is the hard part. And as part of this, part of the pattern, you need a certain lattice walk. And so you can ask how many different types of lattice walks there are, how many different types of patterns you could come up with. And you see here, there's sort of going from a diagram of threads, which is how someone would actually construct this lace, all the way on the right-hand side, Veronica actually did the lace and took a photo of it. So again, these types of things you can study in many different contexts. I know I basically have 1 minute left, so I'm going to quickly talk about one final application, which are lonesome matrices. So a lonesome matrix is a matrix, so an array of numbers that contains zeros and ones that's uniquely determined by if you add up each row and each column. So on the left-hand side here, if you add the rows and columns, you get 1, and so you can't tell between the two matrices on the left. But on the right, all those matrices are uniquely determined by their rows and column sums. It turns out that lonesome matrices count something. They count actually many things, more than I would ever have imagined before I started this project. One of the things they count is the reachable configurations in a certain model of a biological network. So there's some people who developed a model called a ratchet network, and they're trying to argue that it can model sort of how certain biological things are created, and they want to know how expressive the model is. They want to know if it can create enough to actually capture what happens biologically. And so to do that, they need to know asymptotics of these lonesome matrices. And so now we're actually dealing with a multivariate problem. There's two indices, n and k, and so you want to know asymptotics as n and k both go off to infinity, and you can find asymptotics. I apologize, I'm out of time, so I'm not going to really stay on this too long. It also turns out to be related to something called the maximum likelihood degree for algebraic statistics. And so a similar thing, you can show some kind of limit theorems for this problem in statistics. But you can come, the slides will be posted, so if you find this interesting, you can just come and look at this at your leisure. Also, two more recent applications I wanted to mention. DNA storage, so if you want to store information in DNA instead of storing it on a hard drive for long-term storage, it turns out that this is a very active area of research. And so using different techniques, transfer matrix methods, spectral graph theory, and analytic combinatorics in several variables, so multivariate analytic combinatorics, we were able to give certain bounds for how you can encode sequences using DNA in the ways that people care about. And there's another application here from physics, quiver gauge theories. I don't really understand too much about the physics, so maybe I'll just skip that one. But as you see here, you also use techniques from all these different areas of math. So just at the end here, to summarize my final slide, in enumerative combinatorics, we encode properties of discrete structures in sequences. Then we encode sequences using generating functions, and this allows us to apply tools from many areas of pure mathematics to study generating functions. And so if you are interested in enumeration, you can learn and use cool results from all areas of mathematics. So you get to see all the best that math has to offer. You get to apply them to cool applications. So you get to see many different areas, many cool things like that. So I hope everyone found this very interesting. If you found this talk interesting, I will note that this talk was mainly modeled on a set of lecture notes that I developed. So if you go to enumeration.ca, then you can find the full set of lecture notes that goes through everything I talked about here and more. If you're interested in my other textbooks, which are more advanced, next would be an invitation to analytic combinatorics, and then finally analytic combinatorics in several variables, which is sort of the groundbreaking research that we're doing now. So anyways, thank you for your attention, and I'm sorry for going slightly over time.
Thank you very much, Steve, for this really beautiful talk. Great theory and fascinating applications. So now it's time to take some questions. So all the participants already know how this works. So you can type in the chat your questions. So already some questions. So let me tell you the first question. So by Abir, can the lattice walk be used as a study frame to optimize the waiting time in a queue? And if yes, can you give any explanations on how this can be used?
Yeah, so people are interested. One major application of lattice walks is to queuing theory, and so people would try and you try and predict the large-scale behavior of these lattice walks. And so in particular, you could have different configurations, like different number of servers of different people coming in at different times, and you could figure out things like the waiting time for how long you're there, things like that. So I don't really have anything prepared for that, but I will say that yes, it's a major application, and a lot of the theory was developed by people who are interested in queuing theory. There's a lot of work from the probabilistic side, and then also from this combinatorics side, where you're using these generating functions and things like that. So.
Okay, so let me see. Another question is the following. When saying generating functions form data structures for sequences, is there any other ways than generating functions to store sequences?
Is there any other way from generating functions than generating functions to store sequences?
Yes, to store sequences.
Yeah, so I think I mentioned there's recursions. You could have explicit formulas. Yeah, I should also mention there's other types of generating functions. So there's things like Dirichlet generating functions, which are slightly different, exponential generating functions. So the generating function is one tool that you can use. It's basically a way of writing down a sequence in such a way that you can apply techniques from algebra and analysis, and it works well. But that does not mean that it's the only way. So there's certainly other ways that you can try and write these things down. And there's also many different ways of encoding generating functions. So I mentioned some classes here like algebraic or rational. Some people would like to encode them using integral equations or many other different types of representations. So yeah, this is one way that works very well, but of course there's many other ways. And what I tried to focus on today was things that work for a wide variety of cases, a wide variety of different applications. But for many applications, people really care about them and they're very hard. So people develop specialized methods just for one type of problem. And people work for decades just on one type of problem to develop one special kind of representation that they then study the heck out of. So I focused here more on the broad theory as opposed to focusing in particular on one aspect. But yeah, there's many different things that you can do to study sequences, and they're all very beautiful, I think.
Thank you. So during the talk, the following question was also asked: why one would want to encode a generating function as a differential equation?
Well, sometimes you can't encode it using other methods. So for instance, if you have the generating function for north, south, east, west in a quadrant, you can't use an algebraic equation. You can't write it down explicitly as a rational function because it's not algebraic or rational. So you need some way to write it down. And differential equations turn out to be a convenient way of doing it. In particular, you can use these techniques from analytic combinatorics to go from a differential equation to asymptotics in many cases. And so what you're really interested in asymptotics, you use this differential equation as like an intermediate step that you use to go from the starting of the problem to the final asymptotics.
Let me see, there are more questions. Yes, so there is a question by Lisette. How can we realize that an algorithm is biased if we only see the results it produces?
So I'm not sure what you mean by bias. I guess there's many ways to be biased, but I mean, if you're trying to figure out the long scale behavior, I guess this is maybe more a question for a statistician if you're trying to observe the outcome of an experiment and figure out what's going on there. So for me, I'm interested more in studying the discrete structure when you sort of have access to what's going on. But yeah, it's also an interesting problem if you just see the output to figure out, if you just see a sequence of coin flips, how can you figure out if it's a biased coin or not a biased coin, things like this. So this is, again, more in the realm of statistics than probability or combinatorics, but you can use these tools because, for instance, you can figure out, let's go back to coin flipping, you can figure out many different properties that a random sequence of coin flips has, and you can test to figure out whether or not a sequence that someone gives you has these properties, and you can check whether or not it matches. And if it doesn't match some properties, if certain properties are very off what you would expect for a random sequence of coin flips, you could expect maybe I have a biased coin. There's actually a very interesting anecdote, which is in Analytic Combinatorics, the book by Flagellé and Sedgwick, which is, I think it was in Russia. There's a mathematician went to a school and he split the students in the school into two groups. And he told one group of students to flip a coin 500 times and record heads or tails. And he told the other group to write down what they consider to be a random sequence of heads or tails, but not flipping a coin, just coming up with it in their minds. And then afterwards, he tried to figure out which came from the group that actually flipped coins and which came from the group that just tried to pretend to come up with randomness. And in this case, one of the things that he noticed is that people who write down what they think are random sequences don't like to put a great number of heads or tails in a row. So the largest number of heads in a row, if someone's just writing it down, would probably be only 3 or 4. But if you have a very large sequence of random coin flips, eventually you'd get maybe 5 or 6 or 7 or 10 heads in a row. But people don't like to write that down because they consider it to be biased. And so by studying the combinatorics of the problem, you could figure out, say on average, what the maximum number of heads in a row would be if you flipped a coin 500 times. And then if you look at some actual data and you see that there's no more than 3 heads in a row at any point, that could kind of tip you off that maybe there's some bias or someone's kind of fooling around. So again, for a real answer to this question, you should ask a statistician, but you can do things by looking at the large scale behavior of patterns in certain kinds of structures to give you some kind of test for this.
Okay, thank you. So yeah, there's a question by Miguel. Would you recommend any book for getting into generating functions?
So of course, enumeration.ca is my lecture notes that I am biased to like. But there are other books that are very well known and well received. So for instance, there's a book, Generating Functionality by Herb Wolf, which is very nice and many people use to first get into generating functions. The book Analytic Combinatorics by Flageolet and Sedgwick is nice. It is quite advanced, so if you don't have as much of a background in mathematics, if you're just in high school or starting at university, it might seem a little intimidating at first, but I think that's also a very beautiful book. If you go to enumeration.ca, on the front page, I believe it lists some books that are also in the similar area. So you can go on there and also get links to other books. The enumeration.ca notes were written for a first-year course at Waterloo, so it only assumes basically what people get from high school, and then a little bit of like a first calculus course, just for the very basics of limits and sequences and series.
Okay, so there are more questions. Let's see. Oh, yeah. So another question about books. Could you recommend a book to understand what is necessary for complex analysis to understand analytic combinatorics?
So first of all, I think complex analysis is a very beautiful subject. So I wouldn't say only try and learn the stuff that you need for analytic combinatorics. I think it's nice to learn a lot of complex analysis. So for me personally, I think there's a book by Henrici on complex analysis, which is a very nice treatment of complex analysis. But there are, there's many books on complex analysis. If you look in my book, An Invitation to Analytic Combinatorics, I have a fairly lengthy appendix to one of the chapters that goes through like a crash course in some of the complex analysis. If you haven't seen any complex analysis before, I don't think this is the best place to go, but it does give references to other books to look at as well. And yeah, if you're looking just for a general complex analysis reference, I think Henrici is very good, and there's other standard books that you can find online as well.
Okay. So there is a question by Emmanuel. May you talk a little bit more about your application in physics? The one that
sure.
you briefly mentioned.
Yeah, so this is related to something called quiver gauge theories. Quiver gauge theories are related to superstring theory in a way that I don't understand, because I don't really know what superstring theory is. But basically, it's a method of describing something about the physical world. And to describe this theory, you have something called a partition function, which describes some kind of state for a certain kind of theory. And in particular, so there's a lot of high-level physics going on, but in the end, what happens is you get a generating function, in this case, this IPQ, which is represented by an infinite product here that involves a determinant of a certain matrix. And so the other authors here, they are more physicists, and they contacted me because they actually saw my book, An Invitation to Analytic Combinatorics, and they said, we have this problem that we're looking at for multivariate asymptotics related to these partition functions and quiver gauge theories, and we're interested in figuring out how you find the asymptotics, and in particular, if you have different types of asymptotics, that says something about the difference in the physical models. And so we use these kinds of techniques from pure mathematics that I've written here, the saddle point method, pentagonal number theorem, and affine root systems to say something about the asymptotics, which then says something about the physical structure. I will say that of all the applications I've talked about here, this is the only one that the publication is not out yet. So if you're very interested, you'll have to wait a little bit longer. As I mentioned, I have a 1-month-old baby at home, so we should have this hopefully done soon, but it might take a little bit longer because of that. But hopefully, if you're interested in these other applications, you can go on my website, and I have papers of all of them that are available for free to look at, or many of them are also discussed about in my books, except for this one. So sorry that this is the one you found interesting, and this is the only one that's not available right now. But hopefully in a month or two, we'll be done the paper, and it will be publicly available.
Okay, thanks a lot. And apparently there are no more questions.
Oh, good.
So let me thank you once again for this really amazing talk.
Thank you. Yes, thanks a lot.
And yes, so we'll close here the session for today.